Picture this. It is the 1960s. You are standing in a quiet, idyllic suburban neighborhood in California. The kind of classic Americana where kids ride bikes with baseball cards fluttering in the spokes, and neighbors quietly water their lawns. But inside one ordinary, unassuming garage, right next to the family laundry, a high school teenager is secretly building a 2.3 million volt atom smasher. He hasn't simply ordered a kit. He has meticulously scavenged 400 pounds of scrap transformer steel. He has manually wrapped an astonishing 22 miles of copper wire. He is generating a localized magnetic field 20,000 times stronger than the Earth's natural magnetic field. And his ultimate, terrifying goal? To generate a beam of gamma rays powerful enough to literally create antimatter. When he finally plugs it in, the catastrophic power draw blows out the entire neighborhood's power grid, plunging the whole block into absolute darkness. But instead of being arrested or grounded for his natural life, this boy catches the eye of the man who literally invented the hydrogen bomb. This is not the origin story of a comic book supervillain. This is the documented factual childhood of one of the most recognizable theoretical physicists alive today. Welcome to Legendary Lives Unveiled. If you are fascinated by the profound, often tragic realities hiding behind the polished veneer of history's greatest minds, hit that subscribe button, like this video, and share it with a fellow seeker of truth. Today, our mission is to completely unpack the extraordinary, deeply contradictory, and largely hidden life of Dr. Michio Kaku. You almost certainly recognize him. He is the perpetually smiling, highly accessible popularizer of science. The iconic figure with the flowing white hair who appears on every major television network, breaking down black holes, time travel, and the multiverse so the rest of the world can understand. But beneath that cheerful TV persona lies a life forged in the profound trauma of systemic displacement, defined by radical political controversy, and driven by an all-consuming obsession to finish a mathematical puzzle that defeated Albert Einstein. Dr. Kaku's life doesn't just span the modern era of physics. It perfectly mirrors the greatest scientific triumphs and the absolute darkest nuclear terrors of the 20th century. To understand how a child decides to build a particle accelerator instead of playing Little League, we must first look into the shadows of massive societal upheaval. The drive to decode the universe did not start in a pristine, well-funded university laboratory. It started with destruction. Dr. Kaku is of Japanese-Tibetan descent. In the early 1900s, his grandfather immigrated to California for an incredibly symbolic purpose: to serve as a laborer, helping to clean up and rebuild the utter devastation left by the 1906 San Francisco earthquake. The city was in ruins, its districts leveled by fire. It is a striking, almost poetic metaphor for what Michio Kaku would eventually attempt to do with theoretical physics, rebuilding our fundamental understanding of a shattered, fragmented universe. But the family's legacy took a terribly dark turn during World War II. Both of Kaku's parents were born in California. They were American citizens by birth. However, because they were of Japanese descent, they carried a specific bureaucratic label, Kibei. The Kibei were Japanese Americans born in the United States who were sent back to Japan by their parents for their education, absorbing the language and culture before returning to America. Following the attack on Pearl Harbor in 1941, the U.S. government was swept up in a wave of wartime paranoia and xenophobia. The Kibei were viewed with extreme, entirely unfounded suspicion, treated essentially as sleeper agents. This paranoia led directly to Executive Order 9066. The government enacted policies that completely stripped these American citizens of their homes, their businesses, their possessions, and their basic constitutional rights, forcibly rounding them up into detention. Kaku's parents were sent to the Tule Lake War Relocation Center in Modoc County, California. Tule Lake was not a standard internment camp. It was notoriously brutal. The largest and most controversial of all the War Relocation Authority camps, it was eventually designated as a maximum security segregation center. The government sent those they deemed the most disloyal there, a label often applied simply to those who refused to answer a highly biased loyalty questionnaire or who protested the unconstitutional nature of their imprisonment. Imagine the psychological toll. American citizens living behind heavy barbed wire, watched by heavily armed military guards in watchtowers whose machine guns were not pointing outward at an enemy, but inward at the people inside the camp. Yet, inside this unthinkable hostile environment, quite literally under the shadow of guard towers, Michio's parents met, fell in love, and got married. Michio's older brother was born inside that maximum security internment camp. It was a profound psychological crucible. Young people asserting their humanity and building a family in a system designed to strip them of their agency. When the war ended in 1945 and the gates were opened, the government let them out with absolutely nothing. Their previous lives were completely gone. Michio Kaku was born shortly after, in 1947, in San Jose, California. Born into intense, crushing poverty resulting from the financial devastation of the internment, his early life was defined by survival. His father took grueling physical work as a gardener, landscaping yards, while his mother worked as a maid. How does a child born into that level of systemic disadvantage, betrayed and traumatized by his own government, find the psychological safety to dream about the cosmos? Psychologically speaking, when the human world around you is chaotic, unjust, legally arbitrary, and deeply unpredictable, highly intelligent minds will seek out ultimate order elsewhere. The universe does not care about geopolitics. It does not care about barbed wire or xenophobia. The fundamental laws of thermodynamics and electromagnetism are pristine, objective, and purely mathematical. Physics became a sanctuary for young Michio, a place where the rules actually made sense and were unequivocally fair. Furthermore, despite having absolutely zero material wealth, his parents actively nurtured his intellect. They didn't tell him to stop dreaming and get a factory job. They took him to university libraries when he exhausted the local public library. They allowed him to physically take over parts of their small house to build experiments, providing the emotional scaffolding that allowed his mind to wander away from their poverty and out to the stars. This set the stage for a massive global event in April 1955. Kaku was 8 years old when a shockwave hit the scientific community, altering the trajectory of his entire life. Albert Einstein died. It was a massive mourning event for the entire world. Kaku's elementary school teacher somberly announced to the classroom that the greatest scientist of their era had passed away. But it wasn't the mere fact of his death that impacted Kaku. It was a specific photograph published in the newspapers the following day. The image showed Einstein's incredibly messy desk at the Institute for Advanced Study in Princeton, covered in disorganized papers, open notebooks, and pens. The caption explained something profound. On that desk sat the unfinished manuscript of his greatest final work. Einstein had spent the last 30 years of his life isolated from mainstream physics, stubbornly trying to find what he called the unified field theory. He sought a single, elegant equation, perhaps no more than 1 inch long, that would unite the massive scale of gravity and stars with the subatomic laws of the universe. He died without solving it. Young Michio's reaction perfectly encapsulated the audacity of an 8-year-old. Without comprehending the boundaries of human knowledge or the limits of mathematics, he looked at that picture and thought, why couldn't he finish it? It's just a homework problem. Why didn't he ask his mother for help? That innocent, arrogant indignation offended his sense of order. He decided right then and there that he was going to find out what this incredibly difficult problem was. and he was going to finish Albert Einstein's homework. This childhood obsession evolved directly into the mechanical monstrosity sitting in his parents' garage. By the time Kaku was a teenager attending Cubberley High School in Palo Alto, California, he wasn't playing baseball or fixing up hot rods. He was building a Betatron particle accelerator. A Betatron is a specific type of cyclic particle accelerator, the very first machine capable of producing high-energy electrons. Think of a standard electrical power pole transformer, which uses an alternating current in a primary coil to induce a current in a secondary coil via a changing magnetic field. In a Betatron, the primary coil remains, but the secondary copper coil is replaced with a donut-shaped glass vacuum tube. Electrons are injected into this vacuum. By ramping up a massive alternating magnetic field, Faraday's law of induction creates an electric field that whips those free-floating electrons around the donut, accelerating them incredibly close to the speed of light. His goal was staggering: to run Einstein's E equals mc squared backwards. If you accelerate electrons to high enough energies and smash them into a heavy metal target, they release intensely powerful gamma rays. If a gamma ray possesses at least 1.02 mega-electron volts of energy, it can spontaneously transform into an electron-positron pair. Energy becomes matter and antimatter. To build this, he scavenged 400 pounds of scrap transformer steel for the magnetic core. But he also needed 22 miles of copper wire for the coils, which had to be wound tightly and uniformly. This resulted in one of the most charming logistical anecdotes in scientific history. Kaku and his parents lugged massive, heavy spools of copper wire to the local high school football field. His mother took the heavy spool, running from the goal line to the 50-yard line, unwinding it. She handed it to his father, who ran the rest of the way to the opposite goalpost. They spent their weekend winding 22 miles of wire around football goalposts so their teenager could build an atom smasher. His mother's reaction to this absurd reality was incredibly pragmatic. Sure, why not? And don't forget to take out the garbage. When completed, the machine generated a terrifying localized magnetic field of 10,000 Gauss, 20,000 times stronger than the Earth's natural half-Gauss magnetic field. Kaku joked that if you had metal fillings in your teeth, standing near the Betatron would literally rip the metal right out of your mouth. When he finally threw the switch, blowing the neighborhood power grid, it was a reckless, brilliant success. He managed to transport this colossal homemade 2.3 mega-electron volt accelerator to the National Science Fair in Albuquerque, New Mexico. And it was on that sprawling floor of baking soda volcanoes and simple radios that the boy who sought to read the mind of God was approached by the architect of the apocalypse. At the National Science Fair in Albuquerque, New Mexico, Edward Teller was walking the floor. He was looking past the simple radios and the baking soda volcanoes, searching for something more. And then he stopped dead in his tracks. He saw the Betatron. He looked at this high school kid of Japanese descent who had just successfully built an antimatter machine in his parents' garage. And Edward Teller saw incredible, raw potential. To understand the sheer, unsettling gravity of this moment, one must understand exactly who Edward Teller was. He is a massive, polarizing, highly controversial figure in 20th century geopolitics, known to history as the father of the hydrogen bomb. During World War II, Teller was a pivotal theoretical physicist in the Manhattan Project. But while J. Robert Oppenheimer was focused on building the first atomic bomb, the fission bomb, Teller was already looking past it. He wanted more power. He was aggressively pushing for the fusion-based hydrogen bomb, a weapon exponentially more powerful and destructive. Teller was the ultimate Cold Warrior, a man who believed passionately in overwhelming military superiority through nuclear deterrence, and is widely considered by historians to be the primary real-life inspiration for Stanley Kubrick's manic character, Dr. Strangelove, Teller immediately took young Michio under his wing as a protege. He pulled strings and awarded Kaku the prestigious Hertz Engineering Scholarship. This was essentially a golden ticket, a full ride to Harvard University for a boy born into crushing poverty. The optics of this alliance are fascinating, yet deeply unsettling. It was as if a brilliant, innocent pupil, whose sole motivation was to understand the mathematical beauty of the universe, to read the mind of God, as Albert Einstein put it, was being actively scouted, funded, and mentored by the man who built the ultimate weapon of mass destruction. But this was the 1960s. Science was inextricably, intimately linked to warfare and the military-industrial complex. The Cold War was raging. The United States and the Soviet Union were locked in a desperate existential race for technological, spatial, and military supremacy. The U.S. government was aggressively scouting high schools and universities for young scientific geniuses. They needed brainpower. Edward Teller looked at Michio Kaku and saw a brilliant mind that could be shaped and molded into the next generation's premier weapons designer. Kaku, however, did not see it that way. He simply saw a way to pay for Harvard, so he could finally learn the secrets of the universe. And at Harvard, he absolutely dominated. He did not just pass, he excelled. In 1968, Michio Kaku graduated summa cum laude, finishing first in his entire physics class. He was at the very top of the Ivy League, walking a golden paved path, primed to enter the highest echelons of government science or prestigious academia. But the geopolitical reality of 1968 violently interrupted his trajectory. The military-industrial complex no longer just needed scientists, it needed soldiers. In the exact same year, he graduated at the top of his class from Harvard. Michio Kaku was drafted into the United States Army at the height of the Vietnam War. It was a jarring, visceral pivot. He was ripped from debating the finer points of quantum mechanics in the hallowed halls of Harvard and sent directly to basic training at Fort Benning, Georgia. From there, he was sent for advanced infantry training at Fort Lewis in Washington State. He was not being trained to sit at a safe desk in the Pentagon. He was being trained to be a frontline infantryman, a Harvard physics prodigy, a mind holding the cognitive capacity to unlock the universe's greatest secrets, was handed a rifle and prepared to die in the mud of Vietnam. It was a staggering reflection of the indiscriminate machinery of the draft. Yet, a providential medical anomaly spared him. During his processing and medical exams, it was discovered that Kaku had a borderline diabetic condition. His blood sugar levels were abnormally high. He wrote a formal letter to his draft board, pointing out this medical disqualification. Concurrently, the political climate was shifting, the war began winding down, and the military's strategic needs changed. He barely avoided the front lines. As Kaku later recounted, it was as if a voice from above said, "I'm going to give you back your life. You were destined to die on some unnamed hill in Vietnam, unsung, just buried in mud, forgotten by everybody. But somebody up there changed their mind." That terrifying brush with his own mortality, combined with the intense radical political climate of the West Coast in the late 60s and early 70s, triggered a massive ideological rebellion. Listening to early, fierce ecological and anti-war critiques on Pacifica Radio, Kaku experienced a profound, permanent political awakening. This was the definitive moment he permanently rejected Edward Teller's path. Kaku realized that if he stayed under Teller's patronage, his life's work, his ultimate legacy, would be designing the next generation of nuclear warheads to vaporize cities. He looked at what physics did to Hiroshima and Nagasaki. He looked at what the draft almost did to him, and he made a hard, uncompromising pivot. He became a fierce, highly vocal, lifelong anti-nuclear activist. He served on the board of Peace Action. He helped found the organization Asian Americans for Equality. He even co-authored a highly critical 1987 book titled To Win a Nuclear War: The Pentagon's Secret War Plans. He was aggressively protesting the very government establishment that had funded his education. And this activism extended beyond weapons, spilling over into nuclear energy and the use of radioactive materials in any capacity, leading to a highly controversial chapter in 1997 that reveals just how deeply historical trauma affected his worldview. Michio Kaku became one of the loudest voices actively protesting NASA's Cassini space probe. The Cassini mission was a beautifully ambitious project designed to travel to Saturn, orbit the planet, and study its rings and moons. Because sunlight in the deep outer solar system is far too weak for solar panels, NASA had to use RTGs, radioisotope thermoelectric generators. An RTG is not a nuclear reactor. It does not split atoms in a chain reaction. It simply uses the natural steady heat generated by the slow, radioactive decay of a specific isotope, plutonium-238. This heat is converted into electricity with zero moving parts through the thermoelectric effect, specifically the Seebeck effect. By joining two different conductive metals in a circuit, heating one joint while keeping the other cold, the heat energizes the electrons on the hot side, causing them to continuously migrate toward the cold side. That migration is an electrical current, providing a steady, reliable trickle of power for decades in deep space. But to power the heavy instruments on Cassini, NASA loaded the probe with 72 pounds of plutonium-238, the most plutonium ever launched into space at that time. Because of the probe's immense weight, it couldn't fly straight to Saturn. It had to perform a complex slingshot maneuver, flying deep into space, hurtling back toward Earth, and using our planet's gravity to whip it around at tens of thousands of miles per hour to reach the outer solar system. Kaku was terrified. He went on CNN, warning the public of worst-case scenarios. He argued that if the rocket exploded during launch, or if a miscalculation caused Cassini to crash into the Earth's atmosphere during its flyby, it could vaporize and sprinkle deadly plutonium dust over a massive geographical area. He warned that winds could blow the plutonium into Disney World, Universal City, and into the citrus industry, utterly destroying the economy of Central Florida. He claimed potential casualties could run as high as 1 million people. The pushback from the broader scientific community and aerospace engineers was fierce. Critics, thoroughly documented in sources like Atomic Insights, labeled Kaku an anti-nuclear zealot spreading unscientific fear and panic outside of his specific field of theoretical physics. They pointed out that RTGs are phenomenally rugged. The plutonium isn't a single massive chunk. It is divided into small ceramic pellets, encased in multiple layers of iridium and high-strength graphite. They are specifically drop-tested and designed to survive catastrophic rocket explosions and high-speed atmospheric re-entry without leaking. Furthermore, his critics argued that without RTGs, deep space exploration is fundamentally impossible. We wouldn't have the breathtaking close-up photos of Saturn's rings. The Mars rovers would not survive the global Martian dust storms that block out the sun for months. Our understanding of the outer solar system would be permanently crippled. Yet, from a psychological perspective, Kaku's stance makes perfect, tragic sense. Having been directly mentored by the father of the hydrogen bomb, the boundary between peaceful nuclear energy and apocalyptic nuclear weapons was permanently blurred. Edward Teller embodied the terrifying extreme of unchecked physics. Kaku possessed a profound cognitive compartmentalization. He could maintain strict, objective mathematical rigor when dealing with string theory. But his trauma-driven anti-war ideology dictated his terrestrial public policy. He looked at the institutions controlling the technology, remembered his family's internment, and decided they simply could not be trusted with the fire they stole from the gods. Firmly shutting the door on the military-industrial complex, Kaku retreated back to the pure, uncorrupted sanctuary of mathematics. He finished his PhD at the University of California, Berkeley, in 1972. After completing a lectureship at Princeton, he joined the City College of New York, eventually holding the prestigious Henry Samot Chair in Theoretical Physics. He was finally ready to finish Albert Einstein's homework. But as he stepped into the field in the 1970s, physics was at an absolute, catastrophic roadblock. The two greatest, most successful physical theories of the 20th century completely, mathematically hated each other. On one side was Einstein's general relativity, the physics of the very large. It perfectly describes gravity, visualizing space and time as a smooth, continuous, flexible fabric, like a stretched trampoline bent by the weight of stars. It was beautiful, predictable, and smooth, governing galaxies and apples falling from trees. On the other side was quantum mechanics, the physics of the very small. It perfectly describes the subatomic world of electrons, quarks, and the strong and weak nuclear forces. But quantum mechanics dictates that if you zoom in close enough, the universe is not smooth at all. It is violent, jittery, probabilistic, and boiling with quantum fluctuations where particles pop in and out of existence unpredictably, a smooth trampoline on one side, a boiling, chaotic soup on the other. Yet, they were describing the exact same universe. When physicists tried to combine the math of these two theories, for example, to describe a black hole, which requires general relativity for its massive weight and quantum mechanics for its microscopic size, the equations literally blew up. They yielded infinite, nonsensical answers because standard quantum mechanics treated an electron as a point particle, a dot with zero volume. Calculating the gravitational force at a distance of exactly zero required the math to divide by zero. And as any child knows, dividing by zero breaks the absolute rules of mathematics. It yields infinity. You cannot have infinite gravity inside a single electron. The universe was seemingly operating on two entirely different rulebooks, throwing a fatal mathematical syntax error that proved our understanding of reality was fundamentally broken. Dividing by zero is basically the universe throwing a fatal syntax error. It proved that our mathematics were wrong, or at the very least, woefully incomplete. And this is exactly where string theory enters the picture. In 1974, Michio Kaku, along with Professor Keiji Kikawa of Osaka University, wrote the very first papers describing string theory in a field form. It was a monumental, foundational breakthrough. To understand the genius of this, we must look at Dr. Kaku's brilliant, almost poetic musical analogy. Usually, we think of subatomic particles, like electrons or quarks, as tiny solid little dots, microscopic billiard balls. But string theory says no. That point particle assumption, treating an electron as a dot with zero volume, is exactly what causes the math to break down and yield those impossible infinities. If you had a super microscope and could look deep, deep inside an electron, you wouldn't find a dot. You would find a tiny, vibrating, one-dimensional loop of energy, like a microscopic rubber band. Because a string has actual length, it is no longer a point with zero volume. It smears the physical interaction out over space, which mathematically eliminates those pesky infinities. You no longer divide by zero. Just like a guitar string, if you pluck it or twang it one way, it vibrates at a specific frequency. And that specific vibration manifests to our scientific instruments as an electron. If you twang that exact same string a different way, it vibrates differently and appears to us as a neutrino. Twang it again. It becomes a quark. All the hundreds of subatomic particles in the universe are just different musical notes played on the exact same type of fundamental string. The universe is not a random, chaotic collection of billiard balls. It is a cosmic symphony of vibrating strings. Chemistry is the melodies you can play on these strings, and the fundamental laws of physics are the harmonies. It is incredibly elegant. But poetry is never enough in theoretical physics. You need rigorous, unshakable mathematics. Before Kaku's work, string theory was a collection of disparate ideas. Physicists were calculating string interactions one by one, manually drawing tedious diagrams of strings, combining and splitting. It was exhausting and incomplete. What Kaku and Professor Keiji Kikawa did was create string field theory. A field is a mathematical framework that describes how a specific quantity or force distributes and interacts continuously across all of space and time. Just like mapping the continuous temperature of a room or visualizing a magnetic field. Kaku and Kikawa built the complex mathematical framework that allowed physicists to treat strings not just as isolated particles, but as a continuous field. Their equations brilliantly summarized all the infinite possible interactions, movements, mergings, and splittings of strings into one comprehensive mathematical structure. It was a massive step toward that single theory of everything Albert Einstein had spent his last 30 years hopelessly searching for. Yet, despite being one of the pioneers of this massive theoretical breakthrough, Kaku remains incredibly humble about what humanity actually knows. He frequently points out a humbling reality. If you open up any standard introductory physics textbook in a high school right now, the very first thing it teaches you is technically wrong. The textbooks confidently state that the universe is made of atoms, but through astronomical observations, we now know that atoms, the tangible stuff that makes up you, me, the Earth, and the glowing stars, make up only about 4 or 5% of the total universe. The vast, overwhelming majority of the universe is utterly alien to us. It is made of dark matter and dark energy. Dark matter is the invisible scaffolding holding entire galaxies together, and dark energy is the mysterious, relentless force pushing the universe apart. We cannot see them, we cannot interact with them. And honestly, we barely have a clue what they actually are, as Kaku so beautifully and recursively puts it. Physicists are made of atoms. A physicist is an attempt by an atom to understand itself. But why should the average person care? Why spend decades staring out a window, doing hyper-complex math on a piece of paper, trying to find this God equation? Kaku aggressively makes the case that physics is not just abstract philosophy. It is the absolute foundation of all human civilization and wealth. He looks at history and points out an undeniable pattern. Every time physicists unlock a new fundamental force, it alters human destiny. Isaac Newton's mathematics of mechanics and gravity gave us the Industrial Revolution, steam engines, locomotives, skyscrapers, and modern factories. Then, Michael Faraday and James Clerk Maxwell wrote down the precise equations for the electromagnetic force, which completely ushered in the electric age, radios, televisions, computers, and the global internet. The implication is staggering. If we can finally unlock the unified field theory, if we can master all the fundamental forces of the universe in a single equation, what is the next revolution? Finding the God equation wouldn't just be an academic trophy. It could theoretically make us masters of space and time themselves. Realizing that these cosmic truths belong to everyone, not just a few isolated academics in lab coats at Ivy League universities, Kaku made another massive, life-altering career pivot. He stepped out of the academic ivory tower and became the communicator. He realized that you cannot just discover the universe. You have a moral obligation to translate it for the public. His media footprint over the last few decades is nothing short of staggering. He has hosted highly acclaimed documentary series for the BBC, the Discovery Channel, and the Science Channel. He hosts 2 widely syndicated weekly radio programs, science fantastic, and explorations in science, reaching millions of listeners. And he has authored a towering stack of massive mainstream bestsellers: Hyperspace, Physics of the Impossible, Physics of the Future, and The Future of the Mind. In Physics of the Impossible, he takes the wild magic of science fiction, invisibility cloaks, teleportation, lightsabers, time travel, and faster-than-light warp drives, and meticulously grounds it in rigorous science, categorizing them into different classes of impossibility based on real physics. He shows the world how an invisibility cloak could theoretically work today, using metamaterials that bend light around an object, exactly like water flowing around a boulder in a stream. But this futurology isn't just about dreaming up cool gadgets for sci-fi fans. Kaku harbors a deep, almost existential obsession with human survival. When he looks at the paleontological fossil record on Earth, he points out a terrifying, undeniable statistical fact. Extinction is the absolute norm. 99.9% of all life forms that have ever existed on planet Earth are entirely extinct. They are gone forever. Kaku often quotes the science fiction author Larry Niven, who famously declared, "The dinosaurs became extinct because they didn't have a space program." It is a harsh, brutal truth. If a massive asteroid comes hurtling toward Earth, we cannot just stand there and roar at it like a T-Rex. We have to be proactive. We must engineer our own survival. To visualize this cosmic evolution, Kaku utilizes the Kardashev scale, a theoretical framework devised by Russian astrophysicist Nikolai Kardashev, to measure a civilization's technological advancement based purely on how much energy they can harness. A Type 1 civilization is planetary. They can harness, store, and utilize all the energy that reaches their home planet from their parent star. They completely control their planetary environment, controlling the weather, mining the oceans, stopping earthquakes. A Type 2 civilization is stellar. They can harness the entire energy output of their star itself, perhaps by constructing a Dyson sphere, a massive, theoretical megastructure that completely encloses the star to capture all its radiation. A Type 3 civilization is galactic. They can traverse vast cosmic distances, harnessing the energy of an entire galaxy, tapping into billions of stars, and perhaps even drawing immense energy from supermassive black holes. So, where is humanity on this grand cosmic scale? We aren't even on the board. We are a Type 0 civilization. We still get the vast majority of our energy from digging up dead, compressed plants and animals, coal and oil, and setting them on fire. Yet, Kaku argues optimistically that we are currently in the agonizing, violent process of transitioning from Type 0 to Type 1. We are witnessing the birth pangs. The global internet is the chaotic beginning of a Type 1 planetary communication system. English and Mandarin are emerging as planetary Type 1 languages. We see the dawn of a Type 1 culture, with global sports like the Olympics and international media. But here is where Kaku's activism and his physics violently collide. He issues a stark warning. This specific transition from Type 0 to Type 1 is the single most dangerous period in any civilization's entire history. It is the great bottleneck. We have successfully acquired the technological capacity to completely destroy ourselves through nuclear winter, engineered bioweapons, or catastrophic climate change. But we have not yet achieved the societal maturity, the political unity, or the complete technological mastery required to prevent those exact disasters. We are a species with the emotional maturity of teenagers, holding the weapons of gods. To ensure we survive this terrifying bottleneck, Dr. Kaku envisions some incredibly practical, yet deeply futuristic engineering solutions. When he talks about interstellar travel, he does not just idly wait for someone to invent a magical warp drive. He talks about the meticulous mechanics of comet hopping. Surrounding our solar system is the Oort cloud, a massive, spherical shell of trillions of icy comets that extends almost halfway to the Alpha Centauri star system. He suggests we could use these comets as stepping stones, like cosmic lily pads. We could build automated fusion reactors that land on a comet, harvest the ice, melt it, separate the hydrogen, and use it for nuclear fusion propulsion. Then, the ship simply hops to the next comet. It would be a cosmic Route 66, hopping from one deep space refueling station to the next, slowly, methodically bridging the unimaginable gap to the stars. And if the biological human body evolved for a 1G environment with specific atmospheric pressure, is simply too fragile to survive the deadly cosmic radiation and the vast, punishing distances of deep space travel. Kaku talks extensively about digital immortality. We simply don't send the biology at all. We upload our connectomy. The connectomy is the complete, comprehensive map of every single neural pathway and synapse in your brain. All your memories, your personality, your consciousness, everything that makes you, you. Kaku theorizes that once we map the connectomy and acquire sufficient computing power, we can digitize our consciousness. We could then beam that digital consciousness via lasers at the speed of light across the galaxy, to be downloaded into advanced mechanical avatars waiting on distant exoplanets. It is like sending an email of yourself. We could explore the universe at the speed of light, entirely bypassing the fragile limits of biology. But what does this all mean for us, sitting here today, stuck in traffic on a Tuesday? Are we just waiting around to either get wiped out by a supervolcano or eventually, centuries from now, achieve this godlike Type 1 status? Kaku warns fiercely against the danger of passive futurism. It is so easy to read these sweeping books, think about how crazy the future will be, and then go back to mindlessly scrolling on our phones. He ties his grand visions of the future directly back to immediate, urgent activism. He issues stern warnings that nations can easily slip into complacency, anti-intellectualism, and ruin. He emphasizes the absolute importance of basic research, arguing that because pure science is the fundamental engine of all economic prosperity, any nation that actively turns its back on science, that cuts basic research funding, or that demonizes intellectuals, enters an inevitable, fatal downward spiral. And his warnings are deeply rooted in a profound historical empathy. You can hear the tragedy in his voice when he brings up the legacy of Alan Turing. Alan Turing was a genius British mathematician during World War II. He cracked the Nazi Enigma code. Historians estimate his work effectively shortened the bloodiest war in human history by years, saving millions upon millions of lives. Furthermore, he laid the fundamental theoretical groundwork for all of modern computer science. He is a global hero, but his story ends in unspeakable tragedy because Turing was homosexual in a society that criminalized it. His own government, the very government he saved, arrested him. They forced him to undergo chemical castration, leading to his tragic suicide. It is a horrific, shameful example of a society destroying one of its greatest minds simply because of institutionalized ignorance and bigotry. To Kaku, Alan Turing's story is more than just a historical tragedy. It is a profound, screaming cautionary tale for our future. A society must actively protect, elevate, fund, and celebrate its science and its scientists, rather than suppressing them due to fear, prejudice, or short-term political gains. We simply cannot afford to lose our geniuses. The monumental transition to a Type 1 planetary civilization requires every single ounce of human intellect, creativity, and diversity we can possibly muster. We have covered a massive amount of ground. We have explored the physics of antimatter, the elegant mathematics of 11-dimensional string theory, the terrifying specter of nuclear annihilation, and the ultimate cosmic fate of human civilization. But I want to bring us back down to Earth. back to the human being. There is a specific detail about Michio Kaku that perfectly humanizes him, contrasting beautifully with the heavy cosmic weight of his work. Out of all the things he could do in his spare time, his absolute favorite hobby is figure skating. It is a brilliant, unexpected juxtaposition. The theoretical physicist out on the cold ice. The story goes that he started skating when he was taking his daughters to their ice skating lessons. He was sitting there in the freezing rink, realizing he was paying all this money to watch them fall down over and over again. And then his scientific brain clicked. He thought, wait a minute. I am a theoretical physicist. Ice skating isn't magic. It is literally nothing but applied Newtonian physics. He realized that the rink is just a giant physics laboratory. The conservation of angular momentum, the drastic reduction of kinetic friction on the ice, the manipulation of the moment of inertia. All these abstract mathematical concepts he teaches on chalkboards at the university can be physically felt and manipulated with your own body on the rink. The moment of inertia describes how difficult it is to change an object's rotation. If your mass is spread out, it is hard to spin. If your mass is tucked in, you spin faster. Kaku observed that even if you are an absolute, clumsy klutz on dry land, when you step onto the frictionless surface of the ice, the fundamental laws of nature are suddenly working physically in your favor. By simply pulling your arms in tightly, the undeniable law of the conservation of angular momentum forces your body to spin exponentially faster. You don't need magic. You can become an elegant, spinning swan simply by trusting the math. He literally feels the equations of the universe carrying him across the ice. It perfectly encapsulates his entire worldview. For Kaku, physics isn't a chore. It isn't a terrifying, destructive force like he saw in the work of his early mentor. It is a beautiful, elegant, predictable dance with nature. Which leaves us with a truly fascinating thought as we wrap up today's exploration. We started this journey talking about a childhood quest to finish Einstein's one-inch equation, to discover the ultimate theory of everything. But what if Michio Kaku's ultimate legacy in the history books isn't actually finishing that specific math problem? What if his greatest, most lasting contribution to humanity is acting as the bridge? Think about his timeline. He stands exactly between the terrifying, apocalyptic, destructive power of the split atom that defined the 20th century, and the boundless, optimistic, creative potential of the human imagination looking forward to the 21st century and beyond. He is living proof that the exact same species that was clever and cruel enough to invent the hydrogen bomb also possesses the profound capacity to mathematically map the multiverse, to dream of comet hopping to the stars, and to seek ultimate, beautiful harmony in the cosmos. He took the profound generational trauma of internment and the terrifying existential specter of nuclear war, and instead of becoming cynical, he transmuted them into a profound, infectious optimism for the future of humanity. He looked into the absolute darkest parts of the 20th century and chose to show us the stars. If you found this multidimensional exploration of Michio Kaku's hidden life, his controversies, and his genius as mind-blowing as we did, make sure to like, share, and subscribe to Legendary Lives Unveiled. We want to keep having these massive, uncovering conversations with you. Drop a comment below. Do you think humanity will successfully navigate the bottleneck and make it to a Type 1 civilization? Or are we destined to share the dusty, tragic fate of the dinosaurs? We want to hear your theories. Until next time, keep looking up.